The idea then was to think about situations that are similar to this Bellman equation, which basically result in a situation where a function that you would use and an operator that you apply to this function would result in a fixed point, which is then basically the solution, and it would, so that this fixed point exists, and that you applying this operator over and over again would ultimately lead to this fixed point. And this is the basic idea that I tried to explain to you last time. So suppose we have an operator which is called a contraction mapping in a very specific situation, namely in the situation where applied to some functions. In this case, these are two distinct functions, right? So it's v1 and v2, and so this is the v1 and this is the v2, and you have a distance measure, whatever that might be, which is a thing that basically measures the distance between those two functions. And you would argue, or what you would like to have is an operator that if you apply this operator to any of the two functions, that then this distance decreases. Okay, and the idea is now that if you have this contraction mapping, that you could start with any function, okay, and apply the operator on this function and measure the distance between the initial function that you had and the new function that results from applying this operator, and then measure the distance, and then do this again. So apply the operator to the function on which you applied the operator, and then look again at the distance. And you do that over and over again. And what you would like to find is, what you would like to see, and what you would hope for is that applying this operator over and over again will ultimately result in one fixed function, such that the distance between this function and applying the operator again on this function will be what did I say? So the distance between this ultimate function and applying the operator again on this ultimate function will be 0. And this is basically, in a sense, then the solution, okay, to this problem. Okay, so this is the general idea, and I just briefly walk you through this. And we talked about that last time already, and I told you that it's not the goal is not that you have a thorough and rigorous understanding of how exactly the math behind that works, because this is also a thing that I really do not really thoroughly know. So it would be difficult to explain everything in detail to you. But what I would like to for you to take home is that you get the basic intuition behind the algorithm that we will apply over and over again to find a solution to our dynamic optimization problems. Okay, so basically what we do is we start out with some function v. Okay, and the initial function that we start out with is, let's call this the v0. So this is the starting function, whatever that might be. We'll talk about that later on. And we apply the operator on this function, okay, and then compare the distance between the initial function and the function on which results from applying the operator on the v0. So this is maybe from a didactic point of view not the best of all notations. So what we have is the v0, and we apply this operator on the v0. So the v1 is t. So the operator applied on the v0. Okay, and this has a distance. And what we are saying is, okay, when we then move on, so not measuring the distance between the 0 and the 1, but measuring the distance between the 1 and the 2, and those refer just to the number um, of sequences or the number of applications of this operator on this function. Okay, and if you do that, you would see that this distance will become smaller and smaller. Okay, and it will be smaller with a factor beta. Okay, so this distance decreases. Okay, and the idea is that once we apply this often enough, then this distance will actually be zero, and this will then be the solution to an equation that often obviously states that the function and the function that results from the application of the operator on this function will be the same. Okay, this is the standard notion of an equilibrium, or of a fixed point. You just plug it in, and it's the same in on both sides of the equation. Okay, and this is basically at least from my relatively ignorant perspective, the relative basic idea of what is going on here. So we start out with the V0, apply this operator, and measure the distance between neighboring functions as we go along, and apply the operator over and over again. And since since this distance, okay, between the start of two neighboring functions and the next neighboring functions is declining at rate beta, well, for any functions down the line, so if you have if you applied oftentimes enough this operator on those two functions, and you measure the distance between two neighboring functions down the road, and you would like to compare that, well, then you see that it's smaller than the initial distance by a factor beta to the power of n. Okay, because the distance declines over and over again. Okay, so these are neighboring functions. Okay, but you could also just choose two functions that you would like to have. So functions m and n, they do not necessarily be neighboring functions. Okay, so that could be any function. What you want to have is, this is called the triangle inequality, which this distance measure should fulfill. Namely, it just tells you that the direct distance between two functions, okay, in any ways how we measure this distance, okay, is smaller than any detour up to which you reach these two functions. Okay, so this is basically the idea that you have. So the direct distance, this intuition, is smaller than any detour, irrespectively of which detour you take. So this will be considered a good measure, right? So think about a Euclidean distance between 2 points, right? Then it's also the minimum distance that you could find between those 2 points, because they lie on a line. And this is the same, basically. Okay, so if you then use this inside and this inside, you can write the distance between any two functions m and n, so not necessarily neighboring functions, as a function of the original distance, and this is just then a function of the betas. So you would you express the distance between that you just would choose as a function of neighboring distances, And then you plug in here this this result, how neighboring distances evolve. And plugging this in, then you could express the distance between any two functions, okay, as a function of the initial neighboring distances times this this shrinkage fraction, so to say. And what we then have, or then the idea is that if you take any two functions and they are far enough down the line, so you have applied the operator over and over and over again, and you take two functions where you, in the one function you have applied the operator m times, and the other one you have applied the operator n times, that then this distance will converge to 0. Okay, because if m and n are large enough, and remember that the beta is between 0 and 1 by definition, this is the definition of a contraction, so that this so these two functions contract along the way, that this distance then will converge to 0. And this basically implies that if we just start with any function v0 and apply the this contraction mapping operator oftentimes enough, it will be true that there will exist some limiting function v, which is the fixed point of this problem, and the fixed point is defined such or in a way that this fixed point function on the one hand and the operator applied on this fixed point function on the other hand will be the same. Okay, so those two things would be identical. And the general idea would now be the following, to take you back to the Bellman idea. So remember for a second this v and the operator applied to the v. Okay, and this looks relatively familiar, what the Bellman equation does, right? So if we go back here, we have repeated here again, but if we go back to the slide with the Bellman equation, there it is. Then we have something relatively similar. No, there's this functional form, and you apply some operator on this functional form. And the idea is, if this operator, so this maximum thing and this construct is a contraction mapping, so if this operator, so this what you do on the right hand side of the equation is a contraction mapping, then it will be true, or then two things will be true. First of all, there exists some functional form such that this functional form and this functional form is identical. So this is what we are after, right? This is the Bellman equation. This is the fixed point that we are looking for. This is what we like. This is what we would like to derive, for one. And secondly, applying this operator on any starting function and applying it over and over and over again will ultimately result in this fixed point. Okay, so this is I would say relatively clever once we are sure, or once we can ensure that this operator is really contraction mapping. And I do not want to go into detail concerning this, but the idea is that using a sufficiency condition that is called Blackboard sufficiency condition, it can be shown that indeed this maximum operator, so the right-hand side of the Bellman equation, is indeed an operator that fulfills that is a contraction. Okay, and the idea is that if you have two functions and apply the operator, then the relation between the two functions must result in a specific value of the two functions, or a comparison between the two functions. As I said, I do not want to go into details, and the thing is that the Bellman operator, so the operator on the right hand side of the Bellman equation, fulfills this Black-Scholes sufficiency condition, and as such is a contraction. And this is super helpful because then we know, okay, if we want to find a solution to a infinite horizon dynamic or infinite horizon intertemporal optimization problem, which we call the dynamic programming problem, then the only thing we need to know is the functional form of this value function. And to find the functional form of this value function, the only thing we need to do, so only always in quotes, in air quotes, that we just start out with any function, okay, and apply this operator over and over again until the resulting value function and the initial value function is the same. And here again, you maybe already have the feeling or have the perception somewhat that this idea is very much suitable to use an algorithmic approach. So use this in a numerical fashion, because what we need to do is we need to start out with any function that we think suits us. So anything goes. So you just can plug in anything what you want here. Then you solve this problem, which is obviously a hypothetical problem, because if by chance you didn't guess the correct value function in the first place, well, then what the resulting control is obviously totally irrelevant. But from this we have a new value function, and I show you that in a second in more detail. And then we can take this new value function and do the process over and over again until we reach a situation where the function which we plug in here is the same as the function that results here from applying this operator. Okay. Does that make sense? That's good. So although it seems at first glance a little bit confusing, maybe, but the general idea is I mean, relatively simple. It's tedious if you do it by hand. It's really tedious if you do it by hand, but it's not difficult. Okay, but usually when you come across problems, then it's always the case that you can substitute complexity by more work, right? Which is good in a sense, because the simple work can be delegated to either in former times to other people. Okay, remember the job that people had in the 50s at the National Bureau of Economic Research, just inverting matrices by hand all day long. Okay, or you can put it nowadays into a computer. So that's good. So the challenge always is how to substitute away complexity for say doing more work. And this is what we are basically doing here. And as I said, the idea is relatively simple. So you start with any initial value function, okay? And as long as you do not know as long as you do not have some intuition which form to choose, an easy starting point is always to assume that the value function is 0. Okay, so this is the first guess that you use, and using this you would plug in the 0 into the Bellman equation on the right hand side. Okay, so you would just focus go back to the Bellman equation. You just focus on this side of the Bellman equation, and you would plug in here the 0, and then you would ask yourself, what is the best control that you might want to choose? And this is relatively simple, right? Because this is just driven by maximizing the contemporaneous objective, so the contemporaneous utility. You can take the first derivative, set it to 0, and then you would receive the optimal control. Okay, we know that the optimal control is not the real optimal control, at least not as long as the initial guess that we made is correct. Okay, so what we then have is, sorry that I have to jump back and forth between the slides. What we then have is we just have the optimal control, which is just maximizing the utility function. And using this, we could plug this into, again, the right-hand side of the Bellman equation, given our initial guess, which was 0. Okay? And this then makes the new Bellman equation. So basically, everything what we do here is the operator that we apply. Okay, so we start out with a V0, then we do things, so apply the operator on this construct. And what we then have is we have a new function, okay, which is called the V1 of S. And the 1 and the 0, they do not relate to time, but to steps in the iteration process. Okay. And what you then want to check is whether this and this is identical. Okay, because when it is identical, we know from the from this fixed point that this is the solution. Okay, if we know that V0 and V1 is identical, well, then we are there. Then we know the functional form. But what you see obviously here, and this is again not too difficult, we assume that the V0 is 0. Okay, that this is just 0. So the V1 is the utility if you behave optimally. If the utility, if you behave optimally, is not equal to 0, which is usually not the case, well, then it's obviously not true that the correct functional form that we are after is the 0. But that's no problem, because we have a new functional form, the V1, that we then could apply in the next iteration steps, in the next iteration step. And then we do again the same, okay? We just take this V1, plug this into the right-hand side of the Bellman equation, find the new control path, okay? And then use this to calculate again the second step Bellman equation, so the V2, and then check again, okay, is the V1 with which we started equal to the V2, which results from our start. If it is, well, then we are there. If it's not, well, then we go on. And as you might imagine, doing this by hand is doable, okay, but it requires a lot of work and a lot of experience, because you might already sense here that plugging in all over and over again makes the right hand side with every iteration larger and larger. So you have to collect terms, and you have to have a feeling where to collect terms. So this is very time consuming. So usually what people do when they want to characterize those problems on a pen and paper basis, they guess somewhat the functional form and determine then the parameters. Okay, so what people would do is they would not start with V0 equal to 0, This is what you do if somebody else does the work for you, so the computer. But if you have to write it down, well, then you want to make sure that you make a better guess, because the better guess saves you on iterative steps. Okay, and this is what people do. And sometimes people then also only focus on describing the path of the optimal control. But nevertheless, this recursive structure is very is of great advantage when we solve those problems numerically. But still, and this is I think, at least in my perception, an important point. If you solve those problems, and we will see later on that this is a crucial factor, maybe you wanna pre-structure some things for the computer. So sometimes even then, if you are using the computer, it is a good idea to narrow down the solution. Okay, because remember what when we had this infinite the finite horizon problem. Going through all those loops, and this was a relatively simple problem, right? With just one state, and with how many states, how many wealth situations that we could consider 2000 or so, 2001. That even then it took a while, and this problem will become worse and worse. The more states you have, the more situations you want to consider, and the complexity grows exponentially, right? So it's a good idea if you tackle those problems, even if you tackle those numerically, that you try to get a grasp of how to at least in a sense do it by pen and paper. Okay. Do you have questions so far?
Maybe just another remark concerning the numerics. You might already have seen that there's some kind of similarity to the finite horizon case, but also kind of difference in terms of finding the solution. As you just said, what we need is we have to find the value function, and in the finite horizon case, we had a different value function for each period, and we started in the last period, and then we went backwards towards the current period, which meant that we had to represent in the computer the value function in each period. So that was this whole stack of functions that we had to remember, going from the last back to the first one. While here in the infinite horizon case, in a way, it's much simpler because we only have two value functions that we have to consider: our current guess and the next iterations value function, which we find by working through the Bellman equation. Then we have the new guess, which is then the current one, which we put into the Bellman equation again. So we just loop through this Bellman equation, and we always have to remember just two value functions, the current one and the next one. So in a way, that's much easier. Of course, we might take much more iteration loops to run through, in which case the problem might take a long time to solve. But at least conceptually, I think it's actually easier than the finite horizon case. Yeah, so that's a bit surprising, maybe, hopefully.
But this is only due to the fact that we can use this genius insight from the Bellman equation. That this is just that we just have one thing that describes through time this problem, and it doesn't change in the structure. So that will be helpful. And in an infinite horizon case, stacking infinite numbers of functions wouldn't be too helpful as well. No. Okay. So this is the general idea. The next thing that we would like to discuss is basically some applications or some training sessions to this. we have a direct application of this contraction mapping idea. I think using just doing this by hand. And then we have 2 numerical exercises, I think, although I think we are not, as far as I remember, the linear quadratic programming problem is not, there's no iteration involved. There we just determine parameters, no? I can't remember correctly.
Well, it's a bit hidden. It's an iterative procedure because the Riccati equation has to be solved, and that's done iteratively. But you're right, that's a bit hidden, yeah. And the firm level adjustment cost exercise is quadratic again. So actually, we do not have a real numerical exercise that really illustrates the numerical approach. Thanks for pointing that out.
No, but that was not. This is not. That was not on purpose. That was not on purpose. But I didn't think or was it in the stochastic case? As far as I mean, it's always one year away. But as far as I remember, we have, didn't we?
In the stochastic case, we do. Yes.
Ah, okay. So
yeah.
then I
Not only one, but many. Maybe it's more interesting in the stochastic case anyway. So.
Yeah.
Yeah, but I think the linear quadratic case is also good to know, because it's once you know the linear quadratic problem, which is just a special case, then at least you have a modeling framework at hand that allows you to deal with a large number of states and a large number of control variables.
Yep.
Which is not, for numerical reasons, not possible in the general case. Okay, so yeah, the first exercise is really just working through the different steps again by hand, and or verifying at least that these steps that are given now are correct. And then the linear quadratic programming case is either working it through the theoretical approach, which is exercise A, which you can skip if you like, and then doing it numerically, which is B and C. And exercise, the firm level adjustment exercises from the book by Ljungqvist and Sargent. It's really just copied. And that's a model theoretic application to choosing production plans. So in a way, it's a marketing exercise. All right, so if there are no questions, I suggest we start with the exercise. You start with the exercises.